Alright, so in the last class we were talking about drag primarily. So as I said, the videos are all there on my channel, so you can actually watch it how many times you want. So make sure you watch it. That's going to help, right? So we spoke about drag. Yes, two different types of drag: the parasitic drag, and we have the lift-induced drag, right? So what does drag? How do you overcome drag and kind of fly the aircraft, move the aircraft forward? We use thrust for that. Thrust overcomes the drag, right? And two types of drag: parasitic, lift-induced drag. Parasitic drag is because of parasitic surfaces. There are three different types of parasitic drag. What are the three types of parasitic drag? Pressure or form drag, skin friction drag, as well as the interference drag, and that increases with speed. And now talking about lift-induced drag, that's because of the production of lift itself, a component of which now acts in the direction of drag, and that is what is called as lift-induced drag. We have seen all those things in detail in the previous class. We have seen graphs corresponding to both lift-induced drag as well as parasitic drag with indicated airspeed, and we have combined the graphs together. We have seen the total drag curve. And we know that the drag is going to be minimum at a point where the parasitic drag intersects with the lift-induced drag. At lower speeds, the drag is going to be higher because of higher lift-induced drag, and at higher speeds, the drag is going to be higher because of higher parasitic drag. So you have to come to a point where the parasitic drag and lift-induced drag intersects, and that is where you have the minimum drag. We have also seen the advantages of flying at VMD. So flying at minimum drag, what is the primary advantage? Minimum drag is maximum range. This is all something which we have studied in the previous session. We have revised it. Let's go to question number 122. So yes, so let's go to question number 121 then. So we have actually seen these questions before, but I'm just kind of revising it, starting a bit in between. Which of the following statements on transition point is not correct? So what is transition point?
From where the flow becomes laminar to turbulent.
That's right. So that is the transition. So what is transiting? It's transiting or transitioning from the flow being laminar to turbulent. And laminar is a very orderly flow where one layer is flowing without mixing over the other layer. We have said about stream tubes and streamlines and stuff. That kind of a flow is a laminar flow. When it becomes more like a mix, just like you can think about how the school children go out of their classes with the bell rings. That's more like a turbulent flow. So you must have seen the very ordered march past and stuff, more like a laminar flow, and the other one is more like a turbulent flow, right? Yes. So let's see this here. Once again, we have seen this diagram, so you don't have to draw it. It's already there in the notes, right? So relative airflow. RAF, and yeah, this is a relative airflow. It's hitting the aerofoil here at this point. What can you say about this point? What is the pressure at this point? The static pressure is going to be high. Dynamic is going to be low because the velocity is kind of reducing. So what is this point called?
Stagnation point.
Stagnation point. Yes. Can you see this side of the board?
Yes.
And what
is the meaning of this stagnation?
Stagnation means stoppage or something with stopping, right? What is that pressure called? The high static pressure which you told me it's called as the?
High static pressure.
It's called as stagnation pressure, right?
Okay.
Alright. Now we have the boundary layer. What is the boundary layer? The boundary layer is not so high away from the aerofoil. I'm drawing it a bit exaggerated because I need some space here to show you things. It's actually not this far, it's pretty close to the aerofoil, right? We have a boundary layer above and we also have a boundary layer below. Now what is the meaning of this boundary layer? So, what is it? Tell me, we have seen all those things before.
Maximum limit for the flows, I mean there won't be any flow over it.
So basically an air molecule within the boundary layer will have an influence of this aerofoil or the wing passing through it. While if you take an aerofoil out of the boundary layer, that won't be even aware of this aerofoil passing. So there won't be any change in pressure over an aerofoil or a system that is not aerofoil, system that is here, an aqueous system that is over here, a fluid system that is here. That demarcation is what is called as the boundary layer. As I said, it is pretty close to the aerofoil. I'm drawing it wide apart to make things more clear and not to make it more clumsy. Right now, now you know what happens. This boundary layer on one side and the aerofoil on the other side, this kind of acts like a tube. This is like a tube over here, and we apply the equation or the principle of continuity here. So what can you say about the area of cross section of this particular tube? One side of which is formed by the boundary layer, other side is formed by the aerofoil. So you can see the area of cross section is pretty high here. What happens to the area of cross section as you come towards this point here? It reduces. So the area of cross section kind of reduces, and in this particular configuration, where do you think the area of cross section will be least?
At the point.
Say again?
Chord line, yeah. No, stagnation point, right?
So basically, if I want to find out distances along an aerofoil, it's always better to draw the chord line, because we can talk about distances in terms of chord line, percentage of chord line, right? Yes. So general configuration, where can you expect the thickness to be, the area of cross section to be minimum? Where you have
at maximum thickness.
Maximum thickness. Correct? So the maximum thickness is somewhere around here, and that can be expressed as a percentage of chord line. So correspondingly, we have the least area of cross section right here. Now what happens as the area of cross section reduces? So the area of cross section, we have seen a diagram earlier where the area of cross section kind of reduces from, say for example, if I'm taking this as A1, this is A2. All these diagrams we have discussed in detail earlier. That is why I'm not explaining it much over here. Right? And the corresponding area of cross section I will take here as A3. And for A2,
Okay.
A1, A0. Now you see here, we have just plotted variables for the area of cross section from the leading edge all the way to trailing edge. What can you say about the area of cross sections here? A1 is greater than A3, A2 greater than A3, greater than A4, and the highest one is A0. That right here, right? Now, if you look at this, the area of cross section is kind of decreasing to a lowest point, and then what happens to area of cross section? It kind of increases. Now let's look from this point, a stagnation point here, up to the point where the area of cross section is the least. Now what happens when a fluid, an incompressible ideal fluid, when it flows through a tube where the area of cross section is reducing, if the mass flow is constant, that is the mass of the air molecules per unit time, if it is constant, then what is going to happen to the velocity of the air as it flows through decreasing area of cross section?
Higher velocity.
Yeah, it will increase.
So if I write velocity as V1, V2, V3, V4, right? How can you compare this? V1 is going to
V1 greater than V2.
V1 is less than V2,
be, yes,
V2 is less than V3, and V3 is less than V4.
yeah. So you can see what is happening. Yes, below you can see where the area of cross section is the highest, velocity is going to be the lowest.
Right.
Right? And this is true for an ideal fluid. Ideal fluid is an incompressible fluid, and we assume density to be constant, and we also assume a constant mass flow. Only then this will be possible. We have detailed all these things in equation and principle of continuity. Do you remember all these things? You're happy with
So
that,
at
right?
point A0 is to take the velocity further, so
Yeah, so velocity will be even more over here.
Correct.
Right?
Oh, no.
But this V1 probably would be same here as V1, but this is going to be V0 is going to be even lower.
okay. Till V4 it is highest.
At V4 it is the highest. Correct.
Okay.
Right? So you can see here what is happening to the pressure, the static, what is happening to velocity as you go towards where the velocity is kind of increasing, right? What is the meaning of that? What is happening to the air? Increasing velocity is what is called as acceleration.
Acceleration.
Very good. So the air is kind of accelerating. Yeah, accelerating all the way up there. Right? What happens when the air accelerates? Its dynamic pressure increases. So if you look at the dynamic pressures here, because dynamic pressure Q is equal to half rho, where density we take it as constant, v square. If you look at this equation, we have the velocities here. I can write as Q1 dynamic pressure point 1 is less than at 2, less than at 3, and less than highest at 4. Correct? Because the velocity at 4 is the highest, therefore corresponding dynamic pressure, which is half rho v square, is going to be highest over here. So what can you say about the static pressures if this is the dynamic pressure? That's how it changes. So assuming a constant energy, yes?
Just oppositely.
That's right. So static is going to be the highest initially at the stagnation point, where stagnation pressure is the highest pressure. This is the static pressure, right? And that is what the highest, S2, S3, S4. So I don't necessarily have to explain this. We've already explained all these things. I'm just trying to bring those things back to your brains. That's all. We have seen all these diagrams in detail before. So you can see while as the air reaches at this particular point, as of now at this particular configuration, we can assume that's the point of maximum thickness. The static pressure is the lowest, right? Now, so air accelerates. Now, what happens to the air after this point? What is happening to area of cross section here? From A4 to A0, the area of cross section is increasing. Therefore, what is happening to the velocity? That's it. As area of cross section is increasing, the velocity reduces. Velocity reduces. This is as per the equation of continuity, where total energy is assumed to be constant. Therefore, sum of static and so as the area of cross section increases, the velocity has to reduce. So you can see velocity. So what happens when velocity reduces? It's directly connected to dynamic pressure. Q drops, reduces. And Bernoulli's principle, total energy has to be constant. When dynamic pressure reduces, what happens to static pressure?
Static pressure increases.
See, I have written static pressure as S here. Actual representation of static pressure is P, either capital or small. It's P. Yeah. All right. Is it clear? What's happening? Okay. So from here all the way up to here, you can see the static pressure is kind of reducing. From this point of lowest area of cross section to the point of highest area of cross section, static pressure is kind of increasing. Now, what is happening to the air? As you told me, the velocity reduces, right? So air is now forced to actually flow through a region of reverse pressure gradient. So usually how does an air flow? Air flows from a high pressure, high static pressure to low pressure. After this point, air is now moving from lower pressure to an increasing static pressure. So low to high, right? So what happens to the air? Automatically the air is going to decelerate. Is that clear?
Okay.
It's basically deceleration. That's because it's just like you're trying to move from a lower pressure to higher pressure, something is pushing you behind. That's called reverse pressure gradient, right? I'm just running through this because we have seen all those things. So I assume that you know.
Okay.
Okay? Alright. Yes. That is one reason why. So what happens as the we have said about the Coanda effect, if you remember. Yes, how the air tends to stick on to the very gentle curvature of the aerofoil. That effect is what is called as the Coanda effect. Now, as the air starts decelerating, the kinetic energy, what happens to kinetic energy as velocity reduces? Kinetic energy is half mv square. So as the velocity is, there's a deceleration here, velocity is reducing, the kinetic energy, the energy of the air because of its motion reduces, and therefore it now tends to kind of become more non-uniform. right? So have you noticed that certain systems, they move smoothly when it is faster than when it is slower? You do certain things and that becomes more streamlined and smooth. Say for example, rotating a stone with a string. If you do it very slowly, you probably won't be able to circle it. You have to do it faster. And have you seen how you are able to hold something on your palm like this and you leave it, it's going to fall? But if you keep it here and if you kind of move it faster, it's going to stick on your hand, right? So
we can say that we play through in the childhood or something.
Yeah. So basically here all what you're looking at is a speed. So speed is having some kind of energy that is imparted which will let molecules stick together. For the same reason, as the speed is reducing, the energy is kind of reducing. So the flow which was kind of uniform up to this point. So what is the uniform flow called? The uniform streamlined flow is called as a
linear flow.
It's called as a laminar flow.
Okay.
Right? Now, say again. What flow is it?
Nothing.
Yeah, laminar
I
flow.
was being confused with linear flow or laminar flow.
Linear?
Yeah, I was thinking something here, sorry.
So laminar flow is more like a flow that is more streamlined. So you have different layers like stream tubes, stream lines present, and they actually one flow over the other. The viscosity effect is comparatively lesser. It's more like an ideal scenario, which does not really happen in the nature, right? The lines do not cross each other. So it's more like an ideal flow, as I told you, like a march past, line by line. They do not cross, they go in a line. That's more like a laminar flow. Okay, all right. So, but what happens over this part where the area of cross section increases, velocity reduces, the energy because of motion or kinetic energy reduces, and therefore the air seldom tends to kind of follow the curvature. It becomes more like a turbulent flow, right? So from here onwards, the flow becomes turbulent.
From A4, right?
Yes. So where does this flow change or transition from laminar to turbulent? Yes, Anuj, where does it happen?
At maximum thickness points.
It happens at this point where the area of cross section is minimum.
Maximum.
Area of cross section is minimum,
Oh yeah, it is minimum. Yeah.
right? And where the velocity is maximum. Right? So it's kind of moving from a high pressure to a low pressure, and from here it is now moving from a low pressure to a higher pressure. So the pressure over here is going to be higher. The static pressure P is actually higher.
So like when you say like P, static pressure is higher, so mean what thing is happening on the aircraft at this situation? Static pressure is higher at this point.
There is higher concentration of air which is kind of hitting that particular surface. So static pressure, what we discuss here, is primarily because of the bombarding of the molecules with the surface. So you can see here, the static pressure is high here. Why? Because the air molecules are kind of hitting straight. Kinetic energy reduces because velocity reduces, but static increases. But over here, static reduces because the air molecules are moving so fast here, it doesn't really have time to impart energy to the surface because it's just passing faster. As it reaches, it becomes slower and slower, and therefore the static pressure is increasing.
The static pressure is increasing.
Increasing, yes, because the area of cross section increases, velocity reduces, dynamic pressure reduces, total energy has to be constant. So we neglect all of the losses, and therefore we say static pressure now increases. So ideal scenario. Practically there are changes.
But then how the static pressure is higher? Because at the front part of this, the static pressure is higher, no? That you just told.
Yes, and static is lower here. The static is also increasing all the way to the trailing edge. How is it higher? Because the air molecules are moving. What happens to the speed of the air molecules here? Towards the.
It is decreasing.
It is decreasing. So now the air molecules can actually be here for longer time and impart a bombarding force of static pressure on the surface.
Okay.
Over here, the air molecules are moving so fast, it doesn't really have time to kind of sit on the surface.
Okay.
And therefore, static is lower here and higher here. That is more kind of easier to visualize.
Okay. And dynamic is higher here at this point. but dynamics is lower here at this trailing edge.
Correct. That's why static is high. Right?
Okay.
Alright, so this point where the flow transitions from laminar to turbulent, what's the point called?
Transition.
This is what is called as the transition point. Is that clear? Transition point is where the flow changes from streamlined, which is laminar, to turbulent flow, which is more like a flow that is crisscrossing. So it's not very linear, as you said, and the flows, the layers also, they kind of cross each other. There is more influence on the viscosity and stuff. That is the flow. Okay, now think about this. The air is kind of laminar here. It becomes more turbulent all the way here. Now think about a different scenario.